Just write these numbers down and it'll be fat. And again, when you do these explanations, make them in your words. A lot of times, because I know kind of how you all talk, and if you start coming across as the Queen's English, I'll probably burn you on it, because I'll just type in a few words on Google and they'll show up. Just like that, with somebody else's research paper. Hey, Justice, come on over here a second. There you go. Fill that out for me. What I need is to have you go this part here and your signature here, anything that's short here.
Okay.
And I need that back tonight before you leave.
Okay, sounds good.
Okay, so I do check your work, and Google works really bitching for that. So if you think you want to try me, go ahead and do it. I've got a half a dozen guys running through the program, running strong, thinking they passed, and little do they know that they haven't. Their project was worth shit. So know that they're going to have to redo it, and they're going to be standing there with that long puppy dog look on their face, with that wanting that certificate because they got some cool job, and I'm going to be saying, "Oh, baby, well, you got to do your own work. You can't use somebody else's work." So know that I do check. So when you do this, make sure it's your words when you're doing this. Now, I understand you're not artists. If you want to trace something and draw it, that's okay with me. But your words, I want to know what you're thinking. Okay, so you're going to have to do number 1. You have to do number 2. I'm not going to make you do 3.
What is 3?
4. Just write the number down.
Right here. 2. You're not gonna. You said not number 3.
Yeah, you're going to be doing 1, 2, 3, or 1 and 2. 7. 6 you're already doing sort of out in the shop. 5. You'll have to do 5. That's the one with the pretty circles. Pretty colors. So you're doing 1, 2. 1, 2, 5, and 7. Okay?
You want the notebook one? The 7?
7's a notebook.
Yeah.
Yes.
I just thought it was ironic because in the turbines you don't want to do the notebook one.
Okay.
It's okay? Yeah, good. Okay, so we're taking a notebook in here. Pretty simple. I try to keep it as easy as possible. A couple of these projects they turn into real messes, so I'm going to stay away from those. So everybody get those done. A couple of those are handouts. I'm sure some of you, your dog ate them. So I've got some extras if you need some. Get a hold of me. So let me get the roll here. Let's see here. Alan, there you are. Andrews, Sonia, Serrera, here. Colvin, Farmer is here. Ford is here. Hildebrand is here. Jude is here. Kennedy. Kepke. Block is here. McGott is here. And Scalco's here. Manning, I saw him earlier. Rose here. Morgan, there you are. How's your back? Yeah?
They just want to pump pills in me, so I walked out.
Oh, okay. You're kind of the way I am. I don't like pills. Taro's here. Pinzon here.
No storage shots?
Sandoval.
Here.
I get storage shots.
Sellis. Stafford is here. Ten Broom here. Trigg is here. Watts is here. And White. Okay, so we got a few loose ends floating around here.
There's obviously something wrong.
And we're gonna work our way through them here.
I don't think so.
Get this thing up and running here. I'm going to talk about cubic inch displacement here. So we talk about 0320s, we talk about 0360s, 0540s, and all that kind of stuff. And where does that stuff come from? It's going to be a little shorty tonight for you. And we'll kind of wrap it up next week and maybe do a review. I wanted to talk about horsepower and torque. I was gone part of last semester and my substitutes didn't copy the PowerPoint. They stole the PowerPoint right off of my PowerPoint here, so I've got nothing to show you. So I'll rebuild that. And I will do that next week. Just fix up the pacer a little bit. Okay, let me get that back up going here. Actually, just leave that down. Now, I was thinking about, did we didn't have a test in this class, a second test, did we?
No.
Yeah, so that's gonna be your gift, but, maybe that's a good thing, maybe it's a bad thing, I don't know, but it gives us a little bit of extra time here to talk about some of this other stuff. And, this stuff certainly will be on the final exam for you, which is just a couple weeks away. So, so pay careful attention to this. So every engine has a cubic inch displacement. What that means is how much air the piston actually moves. In a theoretical sense, there's always a little bit of loss because this thing's like a big air pump. And it's how much air the entire engine, all 4 cylinders, will displace in one cycle of the engine. One cycle of the engine, how many revolutions of the crankshaft? 2. 2, okay, on a 4-stroke cycle engine. Okay. All right, so a couple of things you need to know is what's the bore of the cylinder, and also the stroke of the cylinder. Now this is simple math. So I want you doing the math, Ed. I want you doing the math with me here. Put paper out. Write this down. Okay, just simple math. But I'm going to throw some crap at you on the test. It's not going to be this easy. So you're going to have to kind of work your way through this, right? All right, so it's the amount of air the engine will displace in one full cycle. So you need to know the cylinder bore, the piston stroke, and the number of cylinders. So we'll stay with something kind of easy here, a little 4-cylinder engine. Okay. Now you could take a picture of this, or you can do it the easy way. And the easy way, I'm going to show you the easy way. So you can remember this big, long formula, but there's a practical way to do it. Like everything, there's a practical method to do it. Right? So the equation is the stroke times half the bore times pi times the number of cylinders. Right? It's the bore squared. Okay. So how do you figure out the area of a circle? So that's the bore is what we're going to start with. The area of a circle. Okay, so that you want to find the area of a circle, use pi times the radius squared, pi r squared. Right, so it's an old joke. Pi r not square, pi r round. Maybe that'll help you, maybe it won't. But know that pi r squared is the way you find the area of a circle. Once you've found the area of that circle, how long is the stroke? How far does that piston move? And you just multiply the two together, and you end up with the total displacement of that piston movement. So you've got the cylinder. You've got the cylinder, but the piston doesn't go all the way, as you know now, from poking your fingers through the spark plug holes. The piston doesn't go all the way to the top of that cylinder. You'll leave a little bit of space up there, up here, for the compression to occur. So this is compression up here. And the piston is going to move from this point here down to this point here, and that's going to be the stroke. Everybody draw yourself a little picture there, because this is going to be important. Now, of course, how do we get a stroke on a piston? We know we got the bore size. How do we get a stroke on the piston? What sets the stroke on the piston?
Crankshaft throw.
Crankshaft throw? What does that mean? Somebody else. What does that mean? Crankshaft throw.
How far offset the rod bearing is from the crankshaft?
From the center line of the crank, right? Yeah. So the crankshaft pivots around the center line, right? Center point. And you have the offset that the connecting rod is attached to. It's called the rod bearing, right? Or the rod throw. So if it goes 2 inches this way, and it goes 2 inches this way, you've got a stroke of 4 inches, right? 4 inches, okay? So that's where you get the stroke. Now, let's plug some numbers into this. In this case, this is going to come up as an 0360. But, and you're welcome to run these numbers just the way they are if you got calculators out. But let's do it my way. It's a little easier, I think. So we're going to take the area of that circle. Pi times the radius squared. What is pi? We'll just keep it simple.
3.14.
3.14. Okay, so we're going to use that number here. That's going to be pi times the radius squared. So if we've got a radius is what? Half the diameter, right?
So
Half the diameter. So this thing has a bore of 5 1/8 inches. 5 1/8 inches. So American cylinders
16.
tend to come in 1/16 of an inch increments. The communists, they come up with all kind of weird numbers, but so far as the United States goes, everything's kind of 1/8 increments. So you can figure that a 1/16 of an inch is 0.063 and change. Okay, so if you've got an 1/8 of an inch, it's 125. It's twice that much. Right? So we've got a bore of 5 1/8 inches. Divide that by 2. Run your number. Go ahead and run your number. Come on, somebody look interested. Somebody, for God's sakes, look interested, please.
2.56.
2 point what?
2.562.
562. Sounds good.
2 7/8.
We're not gonna work in sixteenths or eighths here because it starts getting too cacked up.
7/16.
All right.
7/16. There we go. Try again.
Yeah, it's just, you start screwing around sixteenths, it'll get you in trouble.
Yeah.
Stay with the decimals. Okay, so we've got the radius of this thing. This is the diameter, actually. So the radius of this thing is 2.562. Square it, multiply it against itself, and you'll come up with some number. That number is not important at this point. Should be 4 or 5 inches, something like that. Anybody, come on, using your calculator for God's sake.
6.56.
6 point what?
6.56.
Okay, 6.56. You're gonna multiply that against your pi. 3.14.
20.881.
So what do you end up with?
20.881.
20.881 square inches. Okay, now I got a stroke. I hope your numbers are right here. Now we multiply that number by the stroke. So we've got the area of that circle. That's what we're driving for here, is the area of that circle. Now we multiply it by the stroke. 3.75 inches, which is, or 4.375 inches, which is 4 3/8 inches. Stay with the decimal, make your life easy. 4.375 inches against 20.887. That's 4. What do you end up with? 100 and something? Close to 100? Over 100?
290 something. Is
90.
that 4.345? Yep.
Not too many spaces, just keep it rounded to 1 or 2.
90.16.
90.16. That's one cylinder.
I'm 4.
But we got 4 cylinders here, right? So multiply that by 4.
9 times 6 is 36.
365. 0.41. 251.
It's gonna be 360 something or other.
360 something.
361, I'm gonna call it. (361 cubic inches is displacement). Okay. So this is the method that I use. I find it easier to find the area of the circle and then multiply it by the bore first, or by the stroke. You can go through all this if you want and plug in the numbers little by little, work your way across in an equation. But just from a practical standpoint, I think, from my opinion, is just finding the area of the circle, keeping these things kind of compartmentalized first, and then coming up with a number that's a little bit easier. I don't know about you, but I think that seems to work pretty good. So get on, who's on the internet here? Who's on the internet? Find me the bore and the stroke from O320. Yeah, what do you got?
Why did you times the 20.881 times 4.3 something?
That's a stroke. So the area of the circle is 20.881.
You want volume?
Oh,
And we're going to volume. So we're switching, we have the area, and now we have to add the stroke. How long is that stroke on it then? So what we're doing is we're applying that stroke against that area, and that gives us the volume. total cubic inches for that one cylinder, which it comes out to be 90 point something, whatever it is. Okay. Now, when we run the final exam, you can use your calculators, that's fine. Just be careful that you calculate, that you compartmentalize this stuff, because if you get too many things going on at the same time here, you're gonna end up confusing yourself. And that's why I say just do the area first, times the stroke, times the number of cylinders, yeah.
So for the bore, you want to write it down?
Yeah, okay, so everybody write this number down. What's the bore?
So the bore is 5.125.
So it's 5 1/8 inches.
The stroke is 4.375.
That's the same as my 0360.
That's bigger.
What is the stroke again, I'm sorry?
Oh, sorry. That's my mistake. He was giving you fair.
It's probably like a 5-inch bore, but about the same stroke.
Alright, so the bore is 5.125 and stroke is 3.875.
So it's 3 and 7/8, right? Good. All right, run those numbers. Pi r squared. So we're changing the displacement of this engine. We've still got the same size piston diameter, but the stroke has changed dramatically. So you said it was 5 1/8 inch bore?
Yes.
And a 3 7/8
That's true.
stroke.
Is it more, what was the decimal?
So that's 5.125. And then that's 3.875.
No, I don't care, how come we got different answers? I used 3.142. I did it exactly. Uh-huh.
Okay, so got some numbers there. Okay, so we got a little bit different stroke on this. The bore is the same, so those numbers are still going to work the same, right? The area of the circle, but I took them down. So let's run them again. So if you've got the area of the circle, pi 3.14 times the radius squared. So the radius on this is, let's see, it's a bore of 5 1/8 inches. Radius is going to be 2.5 1/16, so it's going to be 2.5, 2.563, something like that. Okay, so we've got this radius here. Better down. Okay, so we got that for the radius. We want to square it, multiply it against itself. That's how you square a number, is right, just multiply it by itself. What do you end up with?
6.56.
Be a number, somebody?
6.56.
Okay, that's going to be the area. Not yet, because we have to multiply that times 3.14. Now, if I'm confusing you, use that one there. But like I say, I think it's just easier to find the area of that circle first. Okay, what does that come out to be?
20.59.
20.59 is the area of that circle. Okay? Now, what do we do next? Gotta enter the stroke into it, right? So we've got 20.59. Now we got a stroke of 3 7/8, 3.875. Bounce those two against each other and we'll end up with the cubic capacity of one cylinder.
79.81.
79.81. Okay, that's one cylinder. So we got 4,
Correct.
right?
319.27.
What is it?
0.27.
27?
7.4.
I got 5.9.
319.
Más o menos.
Oh,
What
so that-
happened?
You're not gonna really manage the point, manage. the
No,
point.
on your final exam, if you're that close, you're damn close.
Okay.
And what happens, what I told you earlier when we started the classes, a lot of times what happens is the guys in the customer service department and the marketing department, they want you to know that they have an 0320 because 319 and 0319 doesn't roll off the tongue very well. And nobody's going to remember your 0319. But an 0320 will stick in your mind. So they could be over, like that 0360 was, or it could be under just a little bit. Okay? So that's how that kind of stuff happens. Now the other thing too is if you run decimals out all the way or you shorten them up a little bit, that's all going to change a little bit. But if I ask on the final exam, and you come up with a 319 for your number, there isn't going to be an 0322 sitting there. Maybe kind of a gray area. There will be no gray area. It will be that or nothing, right? So if I say, is that an 0320? What are you going to agree with that?
Mm-hmm.
Pretty darn close, right? Exactly. So that occurs pretty easily. Now there's a relationship between this, and this is just the swept area of the piston. Doesn't include anything else in that cylinder.
Doesn't include the combustion chamber.
Doesn't include anything in the combustion chamber. It's just the movement of that piston. And when that piston moves back and forth, let's say I'll have you all lined up here at the door. From this door to that door, you're all waiting to get out here, and I open this door, and I say, everybody get out. And then I slam the door. We can calculate the amount of air theoretically, or the amount of bodies that are going to go through that door, but there's a little bit of startup time. It's like it's sitting at a stoplight, right? The cars ahead of you, they may be nose to tail, all the way to the stoplight, maybe you're the fifth or the 10th person back in that line. And there's adequate time for everybody to get through that light. But you always have the guy at the front who's gonna hesitate. And then you got the second guy who's gonna wait a little bit because he wants like 100 feet between him and the next car. And then you get the other guy who's doing the same damn thing, and pretty soon you get 3 cars through the light. Theoretically, you should get 10 cars through that light, but you end up only getting 3 through. See, you all know what I'm talking about there, right? You all been victimized by this, or maybe been the perpetrator, I don't know. So what happens is, because we're pumping air here, we're closing the valves in those cylinders. When we do that, it takes a little bit of time for that air to accelerate to get going and get into the cylinders. So theoretically, that is how much air is displaced by the piston. From a practical standpoint, you probably lose 10 to 12% of that. Now, how do we get that performance back out of the engine? Well, there's a couple of different ways. So what we're talking about here is just engines that are normally aspirated. So these normally aspirated engines are sucking air in. They're creating a depression in the cylinder, and the air is going to always flow from high to low pressure. So it's going from atmospheric pressure to a lower pressure inside the cylinder. But it takes a little bit for all that to accelerate and get going. So what we do is there's a couple of little tricks we can play on the engine. On a normally aspirated engine, now this is a bone simple engine, nothing tricky about it. We just use a carburetor with this engine. We're also going to add fuel into the air that goes into that cylinder. So you lose a certain amount of air going into the cylinder because the fuel is going to displace some of that air. So that thing doesn't get all the air that it's supposed to have. So you lose that. You lose it from the pumping action where the accelerator, where the piston accelerates and it's trying to draw the air into the cylinder. You lose it there also. So you're going to lose about 10 to 12% on a normally aspirated engine. So if you think that you're going to get 319 cubic inches of air theoretically moving into that engine, it's not going to happen. It just won't happen. What you'll probably end up with is probably something down below 200 and some odd cubic inches of air moving into that cylinder because of the losses from the pumping effect of those pistons. Does that make sense? Yes.
Is this identified as friction loss?
No, this is just simply air movement through the engine. Yes. Friction losses are all going to happen because the rings are scraping and the bearings have a grip on the crankshaft and all that sort of thing.
One way you said you could trick it is to have the exhaust valve open a crack to help with that vacuum.
Yes, so the valve overlap, that's where I was going next. So the valve overlap is super important. So air will entrain. It'll get to be like a train, and all the molecules will follow the leader, one right after another. And as we open and close this door, there's going to be a certain momentum. If the line of you folks was long enough, there will be a certain momentum so that when that door closes, slams, everything stops. But there would be a pressure wave be built up because you'd all be bumping into each other one right after another trying to get through that door, and I'd open that door again. Next thing you know, you'd all be flowing through that door like crazy, and I'd slam the door again, and so on and so forth. So one of the things that we do is that valve overlap period. So what we're doing in essence is I've got another door instead of just one door here, I've got 2 doors. And so I can pre-open one door to allow you to start moving and then open the other door to allow you to continue to flow. Okay? So I can get you going a little bit, keep you moving a little bit, and then we slam the doors. So that's one way we can help defeat that. Another thing we can do is that we can make the intake runners long and narrow. So there's a lot of air always moving through the runners, and if they're narrow, it builds up a velocity inside those pipes so that when the door is open or the valve is open, so you're standing right there waiting for that door to open, the door slams, that pressure wave builds up inside the pipe and helps push that material into the cylinder. Okay? So it's a little bit like supercharging. We're using some pressure tricks here to change the pressure within the intake pipe to allow that material to flow into the engine. Now remember, we've got fuel mixed in with this. We'd really like to just have air. If we just had air in there, the more air we can get in the cylinder, the more pressure we can generate when we do add fuel to it. Now we're talking fuel injection. Now fuel injection can also be normally aspirated. So we're going to be drawing air into the cylinder, but only air. We're metering the fuel. That air goes across a metering valve. How many in Wheeler's fuel induction metering class? Anybody been in it? A couple of you? Okay. Well, what you're doing is you're measuring the mass of the air that goes through what a piece of equipment called an injector servo. So instead of having a carburetor, you have this injection servo. And an injection servo only measures the amount of air that goes into the cylinder, and then the fuel is added at the cylinder. So we're not taking up space, we're not taking up extra space with this fuel. We're adding the fuel right at the end of the trip, right at the door. Okay? And what we're going to end up with is more air and a little bit more fuel than we ordinarily could have in that pipe. The next step up, so this is still normally aspirated induction. The next step up is somehow or other, by a couple of different means, pressurizing the air that goes into the engine. When we pressurize the air that goes into the engine, it's called turbocharging or supercharging or turbo supercharging, depending on how the system is set up. So what we do in that case then is we reduce that lag time, that pumping inefficiency, by pressurizing it. So now all of you are standing in line here, and that door opens. I'm going to be at the back pushing on you. You're not going to wait that 10 feet or 100 feet for that car in front of you. You're going to be right on his bumper when you go through the intersection. Does that make sense? Just another little trick that we can play. Now this adds to the complexity of the engine. Yeah.
Are there any gasoline reciprocating engine or aircraft engines that are direct injected?
Yes, yes, but they haven't become popular yet. And so there's a couple of different ways to inject the fuel. So we have what we use mostly for simplicity and cost is what they call continuous flow injection. And what they do is we drop the fuel into the port, into the intake port, continuously flowing. When that door opens, the fuel goes in with the air that's already sitting there waiting to go through that valve. And what it does, it goes through there, it's sprayed in, so it's kind of a mist, it's kind of a squirt gun mist. It's not really particularly efficient, but as soon as it hits that warm cylinder head and the air hits it, it knocks it into a vapor. Okay. So it's pretty efficient, it's not absolutely efficient. So they have, yes?
In that form, is it being atomized, or is it just?
Yes.
It is. Okay.
Yeah, so they're mixing it, they're pre-mixing it with air, and it's called emulsification. So it's like taking a bottle of gasoline and shaking it, and then it comes out all foamy, and that's what you're going to get in the port. As soon as that air hits it and moves past it, it begins to vaporize it. Yeah. So the next step, yes, ma'am.
So how does that compare to the automotive industry?
How does that what?
Yep.
So
I'll
go
do that
ahead.
later.
No, go ahead.
It was Joe.
A joke about
If you were in Wheeler's class, you got it.
Oh,
How
yeah.
does that compare to automotive injection?
So
Because Honda's doing great.
it's
You know,
Honda's
I
doing
took
great.
that whole fuel meter
Yeah.
class and all we talked about was Hondas.
Yeah.
In
Well, we run our class a little bit different.
Yeah.
To say,
Little bit.
a little bit. You won't hear much about BMWs in my class. The good old days.
Hondas, it was Hondas.
So back to this. So the next step, as Turner was talking about, is direct port injection, or even direct injection into the cylinder. So this is a fairly efficient way of introducing fuel at the correct timing when the engine needs the fuel, not just blowing some fuel in there. So it's timed injection. It's squirted in under high pressure, and it's controlled, usually computer controlled or FADEC controlled in the case of aircraft engines. Now, there's a few of those engines out there now, but every time you do something like this, it adds a level of complexity. to the engine. It adds cost to the engine. So these engines already are overpriced, my opinion. But when you start doing that, you start doubling the cost of the engine. Also, the FAA doesn't have much of an automotive background or history. Some things are changing now. Part 23 and Part 21 are now becoming performance-based FARs, where before you came to the FAA and said, I want to use this, and you had to explain yourself, and you talked about it with the FAA for 10, 15 years, and they may or may not go along with it because that's not the way we've always done it. Now it's become a performance-proven method of getting this stuff approved. The FAA slowly pirouetting and changing a little bit. So you're going to start seeing some direct injection engines, but know that it's going to add to the cost significantly of anything that engine is attached to. So, that's injection. Now, turbocharging, the engine runs, it makes exhaust gas. So we're reclaiming some of that exhaust gas to run an air pump. That's all it is, an air pump, turbocharger. Now, turbochargers suffer from a couple of deficiencies, and one is acceleration, unless they're already running at a very high rate of speed. The automotive guys have figured that out to where they use electric turbochargers for low-end performance on cars. They also use smaller ducting. They'll run 2 turbochargers, so you have dual turbochargers running. But the point here is that you're using the exhaust gas to drive a turbine wheel, which then drives a vane, which then pumps air into the system. So now we are creating a system by where now we are pushing air into the cylinder instead of drawing air in. So you lose, or actually you gain quite a bit, instead of having that about 12% loss of pumping efficiency, now it's upwards of about 5 or 6%. So the more air you can squeeze into the cylinder, the more fuel you can put in the cylinder, for a given displacement, you'll get more horsepower out of it, basically, right? It's the law of slobbering cubic inches. The bigger, more cubic inches, the more horsepower you're going to get out of the engine.
No replacement for displacement.
There's no replacement for displacement. Okay. Now, the other way of doing that is mechanically driving an air pump, and that's called supercharging. Now, supercharging relies on the fact that the engine creates a certain amount of horsepower, because it takes a certain amount of horsepower to drive a supercharger. On a case of a turbocharger, that's all free, because you have exhaust gas anyway. But when you have a supercharger, you're using the engine's horsepower to drive an air pump, and it can take, depending on the size of the air pump, it can take 10 to 12% of the engine's horsepower to drive that air pump, so it better be darn well worth the trouble. A lot of superchargers have shift mechanisms in them, so you can go from a low blower to a high blower or some intermediate speed. So if you're cruising along, you can turn back the blower a little bit. If you're in a takeoff mode, you might want the blower running at full power so that you can carry the most weight off the ground. Now there are combinations of both. There are hybrids of this, that, and the next thing. If you look at this giant engine outside here, what you're going to see is a power recovery turbine. So it added exhaust gas that runs over it, but all it does is drive a shaft that adds to the horsepower of the engine. Doesn't do anything, doesn't run a blower, doesn't run a turbocharger, doesn't do any of that stuff. All it does is run a shaft that's coupled to the engine that helps increase the horsepower. It's a power recovery turbine, okay, in this case. There's a number of different ways you can feed these things. And when we get back off our little break here, I'm going to show you about compression ratios. So let me say this before we go. Usually what happens is the more heat or the more power you generate, the more heat you generate in the engine. At some point, you can start getting into an area where you start having detonation. You all remember detonation? This is the uncontrolled burn of the fuel-air mixture. So you don't want that to occur. So ordinarily, on an engine, those 360s come as 8-to-1 compression ratio. They come as 8.5-to-1. You go all the way up to 10.5-to-1 compression ratio. I'm going to show you what that is when we get back. But what I want you to know from that is that generally speaking, if an engine is turbocharged, they lower the compression ratio slightly to maintain the durability of the engine. So they're still gonna get more horsepower out of the engine, but they have to lose a little bit to keep the temperatures in the engines down. Now, we have all air-cooled engines here. When you have liquid-cooled engines, you can get away with all kinds of stuff because the temperatures are far more stable in a liquid-cooled engine than they are in air-cooled engines. So that works. Yes, ma'am.
Are there any certified liquid cool engines?
Certified liquid-cooled engines?
Yeah.
Yeah, Mustang's got one comes to mind real quick. Not so much other than the diesels, because fit, form, and function kind of dictates that everything is air-cooled in our little universe, our part of the universe. There's a lot of people flying liquid-cooled engines in experimental aircraft. They have great luck with them. But again, once you go with liquid-cooled, you start having to add more layers of complexity. So you end up with liquid cooling systems, valving, hoses, and that sort of thing.
Wait, so you trade weight for,
You're trading one for the other.
The Rotax 912 is what, half liquid, half air?
Half liquid, half air, yeah.
Yeah.
And it only holds a teacup of water anyway.
Yeah.
So, yeah, so it's not such a big deal. Yeah. So why don't you all take 15 minutes and we'll come back and we'll talk about compression ratios.
Yeah.
Did you have a comment?
Yeah, I have it or it's already filled out. All I have to do is sign it. I'm not going to.
eyeballs are good. That's my eyeballs.
Okay, did you guys, by any chance, did you guys able to finish it?
I need to do that. You need to push the airplane, right? Did you push the
Oh,
plane?
score.
I don't even know where to find it. I don't know where to find the information.
In the book, they describe this.
Yeah, but
Basically, this is the
this
cycles.
is what I got a lot of it from the book, but the rest of it I couldn't find it online or anything. You know what I mean? I was just like, did you do this?
Don't worry, Jake, I don't want to go.
Can you?
Did you do this?
you
yet.
want to.
I know.
Like maybe next week, this
I
weekend.
know, so rude.
So, I don't want to do any of this. Homework stuff knocked down and call it a day. Draw a little bit that's that thing. I don't know. So we can do anything. That's the other side. That's this. And then another. So it's only going to be that, it's just balance Hey, is your internet just as bad when you hook on to the nearby Wi-Fi? Do you use the internet here? Is it just as bad for you if you go under the internet? Is it really slow for you too? You need to restart that thing. Get all the catches on. You guys know a lot about anything about internet. Not buying continental.
Yeah.
Content.
just need bigger cylinders, just bigger cylinders and more cylinders.
That was the logic with my 69 Caddy, 472 cubic inches.
That was the logic of the V10, it turned out terrible.
Ford V10?
Yeah, that was a
Yeah,
terrible.
Ford V10's shit, but they still make it. You can still buy a brand new one.
No, I thought they, that's only because they had a, there was a reason behind this, because they were complaining that the farmers were emitting too much, carbon
No,
in the air, so they wanted a truck that would stand it, so they added to it or
it's
something.
just,
To make up for the torque, and it just, they hate it, it's like that.
no, the Ford V10, I'm a Ford guy, but I don't like the front V10.
I think I like it.
It doesn't make enough torque for its displacement. The V8 is better, it fits in smaller packages, and it's lighter. You can get more horsepower out of the V8, you can increase the compression ratio. Also, cylinder heads on those are ridiculous because they're either 3 or 4 valve heads, and they're wantonly complicated and weigh like 100 pounds each, or 150 pounds each.
You know, the new Chevy Silverado. I guess Chevy sells super prices for it. And people are getting like 700 horsepower.
To which Chevy?
Silverado.
What's
It's
the truck?
the new one, the number body style. I don't know what engine it is. It's a V8.
Doesn't work. Yeah, it's probably 60.
How much is that?
What?
On how much that?
Not-
You bought it.
The torque's not great. Well, the torque is good, but the truck can't typically handle the torque. I mean, the diesel versions like the 2500 HD and 3500 HD, those are the whole drivetrain is way stronger on those. Whereas if you get the gasoline powered ones, unless you get a gasoline HD, which you probably did. Well, you can still spend 60. You can still spend 60 grand and get a light duty, like 1500. But
I don't know.
Yeah,
you're better off. You're better off getting get the diesel. Yeah. No, so my dad told me to. So we have an Excursion with a 7.3 in it. You know the old Ford diesel, the one that's indestructible. The transmission's behind terrible. My dad told me that he was driving it over the weekend and the transmission started slipping. I'm like, shit. Because it's going to be $4,000 probably for a new transmission. That's the handle as it is. Of course, then once I put the new transmission in it, then I can turn off on the
See, that's
engine.
what I did 2 weeks ago, so that V10, because it started the transmission and slipping.
Yeah.
And they said it was gonna, here in California said it was gonna cost about $6,000 to replace the whole thing.
Yeah, $4,000 is just for the transmission by
Yeah,
itself.
$6,000
It's without.
for labor and stuff, and I was like, you know what? Definitely not worth it.
No,
In
sure.
1989, V10, piece of shit.
Yeah, so it was the first year of the Super Duty, it was the new Super Duty. The round body style. It's all V10. It's a pretty good engine though. Yeah, it's the one they had in there in the 2500 and 3500 pickups. And it's actually a variation. In fact, the original Viper, the Dodge Viper, uses a variation of that engine at the pickups. Well, the second generation Viper.
Have you seen the new ones?
Yeah, that's the ACR. Yeah, they're awesome. But yeah, the Dodge V10 pickup is basically the same engine. And because that's what the Viper engine came at. It was the V10 pickup, and you can actually the biggest thing about Dodge is although I don't like trucks because they fall apart, you can still get a manual.
Oh, that's.
It's the only
I can't.
manufacturer.
Without paying this, like, $500, you can't get manual from like Chevy. Yeah, and I was like, so we're gonna pay $500?
The problem is that they never offered a manual in the Excursion, and the automatic just can't handle it for it. Because it's my tow rig, it's what I use to, that's the only time I use it is tow it. And the transmission is just going, that's the way out.
it's
I'm back. Everybody, stop. It's so quiet in here.
dude, we're about to go home soon. Did you do this thing?
No, I haven't done that yet.
Fucking, I can't find the rest of the information for it. I actually have an owner's manual online for this car. Years ago, I had to they want. Years ago, I'd have to get it from the Chevy Cobalt dealer, Chevrolet, and then charge you like $500 bucks or $200 something for the manual.
Yeah, my
Are you kidding me? Like, but I bet after a certain age, when they're like, yeah, fuck, we're just gonna get it.
yeah, because I mean, like my Jeep manual, somebody broke into my car like a couple weeks ago.
Yeah.
They took my fucking Jeep manual. But
You fucking serious?
yeah, they took my Jeep manual. But on the other hand, I don't know if they knew that it was expensive. But that fucking manual, I went to Jeep to go get a new one. Fucking $250.
It's ridiculous. Look, this is the same thing I think it is. You got a fucking manual online for free? That's not right. The kid's
Yeah,
gotta
even my what do you call it? I forgot the name of it. And it won't make sense without me. Fuck, I can't remember.
It's ridiculous how much the manuals cost these days. But then again, you know, it's worth it if you're doing the repairs yourself.
Yeah.
Because I gotta pay.
Well, and like some of the stuff, I mean, like, a lot of the stuff, I mean, for the newer cars I know, at least, you can't even do. Like, they have it all, certain shit that have really special tools to get, like, stuff off before you can even fucking start fucking around with shit.
Yeah, that's why I like the older cars better. I want to get a car where I can.
Because I can't, I have a big, huge plastic cover on my engine. It has this special tool you need to get that plastic cover off.
And that tool probably costs $1 million.
Yeah, right.
That's how it usually works, dude.
And if you just try to get it off, it's a clip and it's just gonna snap it, you know?
Yeah.
So, yeah, it
It's
sucks.
bullshit. Look, is it internet? It's bad?
I hate the freaking mirror button.
Dude, it used to be, it's either really fast or really slow. It's never. You do this yet? Auto 4-stroke combustion cycle?
We don't have to do it.
You just said we did. You said.
I thought that's number 4.
You said do 1,
Yeah.
2, 5, and 7.
Okay.
The 1 is the auto cycle.
No, I haven't done the auto.
Label the cylinders. That's that one. That's the auto cycle.
I'm gonna take a
And I'm
picture.
glad we don't have to do the. I just kind of wanted this thing.
Because I had no clue what the auto cycle was. I was gonna start
There's
doing.
a guy named Otto. He designed a system that we know now is the 4-stroke combustion cycle system. And the biggest thing is that it's that for each revolution.
Yeah.
2 revolutions. I don't have that in here though. For some reason. That's alright. It's easy enough.
The only thing I have done for this class is that time. I mean, that diagram.
This diagram, no, this is
I was just gonna get one of. I was just gonna. Honestly, I didn't even know where to find that information. There's like a lot of them online and stuff.
I don't know. I think you have to go under the actual, like Lycoming won't give you the information.
Yeah.
But I think Continental will. So I'm gonna change the engine and just find like in the not the service manuals, but the manuals. Yeah, the manuals. So just pick a Continental, whatever engine model, blah blah blah. And then, here's oh look at this. I can take it forever. I'm still here. 2000. I'll be a 2020. I'll still be. What class you taking next semester?
None.
You taking summer off? You don't? This is it? So you gonna work? Who are you gonna work?
I'm gonna sign up for Delta first and see what they say.
I think it's
But
gonna be.
definitely an airline.
I think it's gonna be a shock to a lot of people. They take all these classes and stuff, right? And then the first year, it's like fucking pushing around and shit like that.
I don't mind. See, just as long as I get paid, just in, I don't
The
care
same
what
as
I
long
do.
as you get paid.
Yeah, just as long as I get paid. So.
Yeah, but I don't wanna. To be honest with you, I don't wanna be pushing a car. You know what I mean? I'm like, I came here, I got all this education for you guys to have me push a drum. Like, how long is that gonna happen? You know? I don't need people to quote unquote break me into a business that way. Fucking, I've been my own boss in my own business for a long time. I don't even know. They treat me like some peon, which they probably will. Like, I don't need this shit. I'm making my own job.
Yeah.
I mean, don't get me wrong. I think that's cool.
Well, I hate it.
We don't have a problem going out there in the real world and working for somebody else.
55.
Yeah. Like,
Going down.
yeah.
Did you get this done?
Not yet.
Nobody's got it done.
I don't get it. I guess you have to look at the, you have to look at the type certificate data sheet of the engine.
That's a type certificate. That's a.
You gotta find out where the.
Yeah.
College trip, I don't even know what we're using, what that is for.
I know.
What Valentine? I don't even remember what it was for, bro, or how you even timed
This
it.
is the Valentine. This tells you exactly what's going on in the engine. And you know what I mean?
So basically, that's
So
when.
this is it. I've got 75 degrees. I looked in the book. Well, they only gave me so much. But information in our books that we got. So officially, you're right. You gotta really check that and look at specifically.
I don't even think that'll have it.
And if it doesn't, it doesn't. I'm just gonna leave it blank. I'm gonna be like, I know, right, but I don't know where to go. Yeah, and that's not my problem. You know what I mean? But I don't know what to put for this trip. Yeah. Valve overlap? I don't know what that is. Like, what do you want me to put for that?
Well, you know that.
Well, I don't.
You know that one rotation is
360
or 360.
360. So that's it. All it's telling you is what's happening at the degree of the cycle.
They have some.
And then when you can figure that
I
out,
was listening to somebody was on the head.
so like 5
No,
degrees.
I'm gonna do-
Yeah, 5 degrees. 5 degrees before top dead center, we got the inlet open. Right? Sure, inlet open, fuel injection, open. It's probably 5 degrees.
I'm further than I am. All I got is top dead center and bottom dead center.
Well, then at least that's a start. That's a start. This manual's taking forever to download.
Yeah. And so then he got out and missed the phone to block all the orders.
Dude, I was so confused about last episode. Second season.
I'm not sure.
Like what I used to say on that one. But it was a little more fun.
Look at it this way. Do you know how many seasons of the top series you get?
Oh, you know, right?
I'm gonna get you have an exam soon.
Yeah.
You have an exam this Thursday?
Yeah, around season 8 or 9 is when they started getting good.
Yeah. We have an exam in turbines?
Nah. Yeah, I thought same thing. I was like, what?
We can meet with this and
I don't think we have an exam with her, but
Yeah, that was like.
we just took that test.
Yeah, yeah.
Okay, let's get started again here. As soon as we're done, we're done.
Excellent.
Okay,
Okay, that means we're taking the test next, final next week?
what's that?
Final next week?
No. No, I got some
Review
more to talk
next
to you about
week.
next week. We'll run a couple more of these displacement questions next week. Well, I want you to start getting used to using a little bit of math in your day-to-day activities. Somebody's going to say, how many cubic inches are in that fuel tank over there? Somebody's going to say, how much hydraulic oil are you displacing in that master brake cylinder? Have you had hydraulics classes yet? A few of you will. So you've already had some of this stuff. And you need to know what the displacement is or how much liquid is being moved every stroke of the pedal or every theoretical stroke of the pedal. On a hydraulic ram, it operates maybe a flap or an aileron. You need to know how far that thing's going to move with a given amount of displacement. And it all translates. It's just simple math. You can see it's all stuff that's pretty easy to deal with. Just try to keep it as simple as possible. And when you're working on this stuff, I do recommend that you put it down on paper, because if you don't, you're going to get yourself confused. I do it to myself all the time. Now, I'm not the sharpest tool in the toolbox, but I know that if I work in an organized fashion, I can look like the sharpest tool in the toolbox anyway. Okay, so let's move on here a little bit. Let's just go to the board. Turn this thing off, get that out of the way. So we know that the piston moves top to bottom. It has what they call a swept stroke, and that is whatever the stroke is. If it's 4-inch stroke or it's an 8-inch stroke or whatever it is, that is a swept space of volume that it's going to displace, theoretically. I know you're always going to lose a little bit, like we were talking about. So the piston's going to go to the top up here. It's going to go back to the bottom. It's never going to change, or hope to God it doesn't change anyway. If it changes, you've got some mechanical difficulties on your hands. So the piston goes up, and the piston goes down. We're going to talk about variable compression. We're going to talk about that. All right, so piston goes up to the top, piston goes down. It always leaves a little bit of space inside the cylinder. Okay, so Tierney, get back on board with us here. We'll be out there dreaming someplace. Got a little bit of space up here called the compression area. There's not going to be anything in there but fuel and air with that piston pushed all the way up, unless it's on the exhaust stroke. If it's on the exhaust stroke, what's going to be left up in that area?
Smoke.
Remnants of exhaust gas. Yeah, exactly. So you've got 2 strokes. The thing goes up and down twice for every cycle. Now, how do you figure the compression ratio on this engine? Compression ratio you only have to deal with on the compression stroke. You don't have to worry about anything else. Don't worry about the exhaust stroke. Don't worry about the valve overlap or any of the rest of this. What we're going to do is we've already got this much here in the stroke. This is the volume. But you've still got some volume left here. So the compression ratio is a ratio of the size of the cylinder, the entire size of the cylinder. And that includes this area up here. All right? So we know that this part here is the volumetric displacement. But what we're talking about here is the relationship of the piston from this point here in this cylinder to this point here in this cylinder. So we're talking about this much. In this case, we're talking about compression ratio. talking about that much of the cylinder. Okay, everybody see the difference between the two? So we're not just talking about the swept area of the piston, we're talking about the entire cylinder in this case. The relationship of how much air do we take in and how far do we squeeze it down. So let's go back to that 0360. We ended up with 361 cubic inches. Now we're only going to deal with this on a cylinder basis. I've had people do it by a whole engine at the same time and then divide by 4, divide by 6. That just, it's going to cack you up. It's just going to screw you up. Just do one cylinder at a time, right? So we've got 361 cubic inches in 4 cylinders. We've got what, 90.25 or something? Is that what it was? Yeah. So we got 90.25. Cubic inches in each cylinder. That's not including this compression space here. Not including that. All right. Now, you're not going to know necessarily what that compression space is going to be. Hot rod guys have a way of figuring this out, and they use liquid. So what they'll do is they'll push the piston into the cylinder about as far as it will go, as far as the stroke carries it, and then they measure that compression space with a liquid to find out what the compression space is in volume. It's easy to do with a liquid because you just pour it into a beaker and it tells you how many cubic inches, right? And because, you know, the top of the cylinders are kind of uneven and irregular, you're working around valves, you've got spark plugs stuck in holes, you've got cooling spaces, you've got ledges and whatnot in there. So liquid is just a super easy way to do it. So what we're going to do is, I've already figured this out for you. In the case of this engine here, we're going to have 12 cubic inches of combustion space at the top of the piston stroke. 12 cubic inches is what that space is going to be confined to with that piston pushed up at the top of its stroke. So the relationship is going to be, compression ratio wise, it's going to be a number. Jesus Christ, everything going out here today.
End of the semester.
I know it. This one work? A little bit. So it's going to be some number to 1. What you're going to do, you already have what I said, it was 12 something?
Yes.
12 inches, 12 cubic inches, no points. Yeah, 12 cubic inches. So you're going to add, and you can go ahead and do this, add this much here, your displacement per cylinder, which was 90.25. Add that number to 12. And what that's going to do is that's going to give you the amount of volume with the piston at its lowest point to the top of the cylinder. That's going to give you everything cubic inch wise in this cylinder from the top of the piston when it's down, all the way to the top of the cylinder head itself. Did y'all do that? 12? 12 plus
102.
102 something?
25.
So that's the total displacement. That's the big number. But we want to find out, we want to narrow that down what the relationship is when we push that piston all the way up. So what are we left with when we push the piston all the way up?
12.
12 cubic inches. So easy peasy, divide 12 into 102, was it?
Yep.
Divide 12
5
into
to 1.
102.
5 to 1 there, but
How many times does this go into this?
8.5.
6 to 1.
8.5. Right, so in this case, our compression ratio is going to be 8.5 to 1, which is a pretty normal compression ratio. They'd call this a high compression ratio for an aircraft engine. You all see that? Now, when I give you the problem on a final, I'm going to give you this compression space here. I don't want you to have to figure it out. You don't have the tools to do that when you try to take a final exam. but know that it is a relationship of the total volume of that cylinder to the volume of the cylinder with the piston all the way up. You see that relationship between the two? So we're taking in that much air, and we're going to squeeze it down to that 12 cubic inches. Now, the reason that you jack up or lower the compression ratio is you get more horsepower in the engine. Also, it starts to take life away from the engine. The higher the horsepower rating goes, unless the engine is built for it. So a lot of these engines that we use are kind of used in a lot of different aircraft. And so, so they try to build one kind of engine, and then they can raise or lower the compression ratio ever so slightly, depending on the application that it's going to be put into. So this would be an 8.5 to 1 would be about 160, 165 horsepower. Excuse me, that's 0360. That would be pushing about 190 horsepower. Most of them are sitting in about 180 horsepower. So you get a little extra 10 horsepower. Doesn't seem like a lot, but in an airplane, it's huge. It's a big deal. Little airplane. All right. You see that? See that relationship? Yeah.
I was going to ask you, what kind of liquid are you putting into the cylinder to be
They can use oil or they can use water or whatever they want. What they do is they turn the cylinder upside down, push the piston into it. Don't use alcohol because it dries up. You know, you're trying to work with it and stuff is evaporating away on you, so it would be self-defeating. But they use something that doesn't evaporate quickly, but will fill all those little nooks and crannies. And when they get it to the proper level, then they pour it out into a beaker, and the beaker's already pre-measured.
So you want to do it with it on the aircraft?
No, you wouldn't do it on the airplane. This is already pre-engineered. This is stuff you don't have to worry about. But what I want you to see is a relationship here. So how would you adjust? And there's a lot of people that do adjust the compression ratio on engines. How would you adjust easily the compression ratio on an engine?
Change the top of the
I'm
piston.
not saying it'd be cheap.
Change piston.
So if you lower the piston, it's going to go lower when it goes down. It's also going to be lower when it goes up. So your compression is probably not going to be changed too much. Yeah.
But today's turbocharging, you can tune your turbo to pull different compression through, no?
No, because the compression ratio of the engine is still going to be the same.
You want to add more? You want to add more air somehow, right?
This is going to have to do with the crankshaft.
You'd have to replace the crankshaft.
Yes.
Just
Longer or
because you have
shorter
to
stroke?
Remove that journal further, closer to the center line.
Further or closer to the center line, and that's how that's done. Is so the stroke is what changes. You can't change the stroke by shortening the connecting rod because the piston's still going to move the same amount based on the probe on the crankshaft. Does that make sense? Yeah. You cut the top of the piston off, you shorten the piston, but the piston doesn't go up as far either. It'll go down further, but it won't go up as far either. So that wouldn't translate into what you're looking for. What you have to do is, this is a big structural change. If people do this, they'll change crankshaft to change the compression ratio. You also find it in families of engines. So there are 0320s out there. Let's go to an 0320 real quick. They will shift the crank pin location. And what that's going to do is you can get 175 horsepower out of an 0320, which is kind of pushing it a little bit. They're not structurally really built for that. But you can also run them down to about 145 horsepower. So by changing that stroke and changing the compression ratio, it's going to change the velocity that the air moves through the intake pipes into the cylinders. It's also going to change the amount of volume of air that goes into the cylinders. It's going to change the heat. It's going to change everything. It's going to change the horsepower. The fuel flow will change. All of that will change because the airflow will change appropriately.
So Lonnie, is that basically what they do when they do the STC conversions? Like from like a 320 to a 180 horsepower
Yes.
conversion?
Yeah, exactly right. Yeah, so they'll change the crankshaft, but you have to change pistons, and you have, because now when you start raising the compression ratio, the pistons start taking a little bit more heat, start taking a little more beating, the engine makes a little more heat. And so all of this has to kind of go hand in glove. It all has to fit together. You can't just change just the crankshaft, although I know people that have done that. And they've had pretty good luck with it. But no, again, when you have to turbocharge something, you've gone from normally aspirated, you're gonna have to lower the compression ratio just a little bit to get away from the detonation. Now, there's some ways to beat detonation. I'm not gonna talk about those here tonight, but know that there are some ways to get around that without having to lower the compression ratio. Okay, so let's go to back to our 0320. Write these numbers down. You've got 79.75 cubic inches per cylinder. We'll just keep this per cylinder, make life easy. Your combustion chamber is 10.5 cubic inches.
10.25.
10.5.
That's just, that's only 1.7. So you.
What kind of compression ratio does that give?
10 divided by.
So with it all the way, the piston all the way at the top, you've got a compression chamber, a combustion chamber of 10.5 cubic inches, right? And down all the way at the bottom, you've got that, what did I say, 70 something?
79.75.
79 point whatever it was, cubic inches. So add the 10.5, right? Add the 10.5 to the 79.75. Add those two together, and that's going to give you the complete volume of this cylinder, the whole volume, with the piston at its bottom of its stroke.
The 8.6 to 1.
Is it volume or do you say compression?
10.5 to 1
Okay.
89.
Then you're going to divide that total number by 10.5.
What do you get?
So what you've done is you've taken this much, you've added the compression space to it, and gotten the full volume. But how many times does that go into this here?
It's 8.6. Something like that. To 1.
What'd you come up with? Anybody?
Like 8.6 to 1 or something?
8.6 to 1, roughly.
Anybody else?
Yeah.
They're all kind of about the same ballpark? Okay, so you see how that works, right? It's just that easy. It's just that easy. Now, we're gonna do one more here. You all see how that works?
Yeah.
Because if you're foggy, you're gonna get one more chance next week to, and you better remind me, because I'll probably forget. Let me give you one more. You've all seen this thing or been around it. I guess I could just go over here.
So just get this right, so it's 8.5 times.
So that's the
compression.
stroke from here to there. So
8.5 to 1, yeah.
And then you're just adding the extra other compression right there. And then you go the total divided by.
Okay, so I got one here, and you don't even have to do the compression ratio on it.
Combustion chamber divided by the total, and that's where you get this.
It's a low compression engine. It's a 9-cylinder radial engine,
Probably 6.5 to 1.
probably about 7 to 1, 6.5 to 1, some kind of low compression ratio. They were meant to burn automobile gas, low octane gas. Which fuel burns faster, high octane or low octane fuel?
The same.
Actually, the low octane fuel burns faster, faster ignition rate. The higher the octane, the more suppressants they have in it to keep it from burning too quickly. All right. So I should turn and must have read something somewhere, but that's the standard that we use. Okay, so you've got a 9-cylinder engine. I want you to tell me what the displacement of this engine is. Okay. So it has a bore of 5 3/16, and it has a stroke of 5 3/16. This is what is known as a square engine. So the bore and the stroke are the same. Remember, 16th is 0.063. Pi r squared.
It's gonna be spoken.
Just displacement, that's all I'm looking for.
Good engine.
450 horsepower, 620 some odd pounds. We have one down at the hangar. You've all seen it, I'm sure.
You owned an aircraft with one in it.
I'm sorry?
You owned an aircraft with one in it, right?
Yeah, couple actually. Yeah. Good engines, good solid, dependable engines.
They were in everything back in the day.
Yeah, they still build them. In fact, there's a company in Poland borrow the tooling from Pratt Whitney. You can still buy parts from them. Give you a couple more minutes here. I'll ask for a show of hands and see what you came up with. How you doing there, Brian? You ready to go?
I was wondering if I can give you my number. I don't know if I'm right or wrong. 986.175.
Pretty damn close, yeah. Anybody else?
985.58.
985. Yeah, it kind of depends on how far out your decimal points go. So always remember that you got a number of cylinders involved in these things. They're not always equal numbers like 6s or 4s or 8s. If you have radial engines, typically they're odd number of cylinders. Be sure you always bounce that number against the individual volume, or you'll end up with the wrong number. Also V engines, same thing. 12s, kind of out of the ordinary. So at final, I'm going to have a number of different little questions like this. And so you can kind of count on seeing some of this stuff again. So we've done the 0360s, we've done the 0320s, so I'll figure out something else for you. Next week we'll run some more of these. All right, so how many got 985 cubic inches? Again, the marketing people,
990.
yeah, they don't want to come up with 986 or.
I'm not doing it.
They do
Yeah,
990.
they don't play that game. And so there's a company called Wright Aeronautical built one called, it was a R975. So they were, we got a bigger engine, we got a smaller engine. Our engine makes more horsepower. The marketing people kind of drive a lot of this stuff. But they never come out dead on. Because if you think about it, the way the step on the top of the piston is, it goes down to the ring. That gets you a little bit of extra cubic capacity, but for theoretical purposes, we don't worry about that kind of stuff. 985. How many got 985? If you didn't, God have mercy on your soul. Yeah. All right, so that's all I'm going to talk to you about tonight. You're out of here a little bit early. Next week we'll do some more of this, and then you can plan on your final the last week of school.